Okay, good afternoon. I'm going to carry on from where we stopped. And there were there were some questions in the previous lab class, previous section, and I'm going to start there. So we may have discovered an error in the homework questions or one of the homework problems. So let me bring that up first. So section 2, right here in this one. Sorry, not this one. I think it was, yeah, it was this problem. So in the homework, this problem, question number 5, it says the load in the schematic is connected to a voltage source. So RL is connected to V, and then there is wiring which has some resistance that is included, that is noted by R line. Okay. Question being asked is find the current. In sub-question A, find the current first. Sub-question B, find the value of the wire resistances if the source is 12 volts, and then the total power dissipated in the wires. So when we try to solve this, let's see. Let me copy and paste. All right. So this is homework 01, problem 4. Okay. What we are given is that the power in the load PRL is 110 watts. RL is 10 ohms. We are asked to find I. Right? Power is given to us. We are asked to find I. So what do you think? What equations? Power equation and Ohm's law. P equals V squared or R, or I squared times R. We have R, we have P power. So we can use the equation. Power P is I squared times R. So we can write I is the square root of P over R. And you solve it, you obtain the value of the current. Well, once we obtain the current, we can see the current is the same for the entire circuit. It's a series connection, right? So the same current must flow through the cable wires. So in part B, the question asks us, what if the voltage is 12, RL is still 10? So what is the voltage across that load resistor? So if you do this calculation, what answer do you get? In sub-question A, what is I? Take out your calculators and perform this calculation. Root of 11, yes. Yeah. 3.3166. I usually go 4 decimal places. What is that? So now if RL is 10, what is VRL? Right? Because it's just 3 times. So 33.166 volts. Yes. This question being asked is, can we leave the answer as square root of 11? Technically, your answer would be correct, but that would not be acceptable as engineers or any place. So as an example, not to like make fun, it's a very valid question. Should we leave it as that? But I'm just saying, not just in this class, just anywhere, we should not leave answers in fractions or in like square root or square or anything. We always must find the final value with at least 2 or 3 decimal places. Because if we are going to buy something for like $3, we never say it's the square root of 9 or square of 5. We always give the final answer, $25.50 or something like that. So as engineers, we always do that. Anyway, so coming back here, what is my supply voltage? It's given as 12 volts. So my supply voltage is 12 volts. There is no way on earth that the load resistor can have 33 volts across it. It's just not possible. There's no way you can have more voltage across that resistor when the supply itself is 12. And so we were trying to solve this. So student had some questions, they got some negative answer, and he went through it and was like, yeah, it's correct. There's some sort of an error. So I need to consult with Dr. Protonov, see if there's an error. And the student pointed out that instead of 12 volts, it could perhaps be 120 volts, 120. So I don't know. At this point, I don't know. So once I have an answer, I will inform the students. In the meantime, if you do want to proceed, try with 120 volts and see if you obtain your right answer. Okay. All right, let's see. One of the two could possibly incorrect. Either PRL is 11 watts. So this value either of those things might have an error. Other than that, the problem would not make sense. Okay. Yes. So the question being asked is, wouldn't we have to account for the resistances? The answer is yes and no, because actually, as far as this question goes, no, because this question states the power that is provided is dissipated only in the load resistor, not for the entire system. It only refers to that load resistor, nothing else. Yeah. There's a question at the back. Uh-huh. So let's see. Problem 4. Yeah. So it's problem. Yeah, it refers to problem 5. Yeah. Thank you. Thank you for pointing that out. Okay. Okay. All right. So that's the Spice verification. How many of you were able to download and install Spice or work? I mean, not Spice, LT Spice, or worked with LT Spice yet? Okay, good. All right. So in LT Spice, LT Spice is based on Spice. Spice is a program that was created at UC Berkeley and released in 1973. A student research project. It itself was based previously on a US government funded project for computer analysis. So in there, we specify everything is referenced to one single reference node, which in LT Spice is noted by this triangular symbol for ground or earth. So without this being present in a circuit, LT Spice will not execute. Every circuit requires LT Spice, okay? So once you have the ground or the reference node as part of the circuit, you run the code. So you execute the circuit diagram, it performs its calculations, comes back with some answers. Now, as soon as you build the circuit, LT Spice is going to assign a node number to each of the nodes that it sees in the circuit. So if you hover your mouse cursor anywhere along this node, it's going to tell you this is node 001, 002, 003, and so on and so forth. I don't know if it shows up in a Mac or not, but in a Windows machine or a Windows environment, once you're on LT Spice, if you take your mouse cursor and you hover on top of this node, in the bottom left corner of that window, in the status bar at the bottom, it is going to show you this is node 001, and it'll tell you the voltage associated with that node. If you hover it over here at the bottom, it's going to show you this is GND, this is ground. It's not going to tell you this is node 0. It'll simply tell you this is ground, this is GND. And it'll say 0 volts. Okay. And then you hover at the top, it's going to show you 12 volts. Here it's going to show you 11.61. And here at the bottom, it's going to show you 0.389. So 11.61 is measured with positive reference here. And negative reference here at the reference node. A positive terminal connected at node C, negative connected at the reference node. That's how it works. If we wish to place the voltage on the circuit diagram itself, after we run the simulation, we can hover the cursor on top. It changes to kind of like a red pen layout, meaning we're trying to measure at that point. And so once you see that pen layout and you click on it, it's going to display this voltage right on the circuit diagram itself. Okay. So you run the simulation, you can verify this for yourself. Hover the mouse, click, it will show the voltage directly on top of the wire. Right. So when we run the simulation for this, well, you already have the results in here. You can see what we had done. Okay. So in the next slides after we finish this one, come on. Okay. All right. So we're talking about measurement devices, ampere meters or ammeters for short, and voltmeters require measurement of voltages. So in 145 in the lab, have you already performed voltage and current measurements? Okay. So let's say we have the circuit that you see here. The circuit is rather straightforward. You have a voltage source and you have a resistor. This is a very unique connection of circuit because These two components are in parallel as well as in series. So the same voltage appears across both components and the same current flows. Same current flows through both components and the same voltage. So it's in series as well as in parallel. Now, if you wish to connect or measure the voltage across that load resistor, you take a meter and connect it directly in parallel with that load. So if we do that, this is what we'll have. Electrical devices all electrical devices can be represented as having resistance at their two ends. So if you take a voltmeter and you connect it in parallel to a resistor and try to measure the voltage, that resistor or that circuit is going to see the resistance of the voltmeter also. So what happens if the resistance of the voltmeter is low? So it'll absorb some current from the circuit. And if it absorbs some current from the circuit, meaning some current goes to the load and some goes to the meter, it's going to cause a voltage drop across that meter. And because the current is being pulled away from the load, now the voltage across that load is going to be different. And so a desirable property for a voltmeter is to have a resistance that is infinite ohms or very, very high. Okay, so voltmeter, it is desirable to have very, very high resistance. Ideal voltmeters should be infinite. If it is infinite, what is the current flowing through that infinity? Zero, right? And so an ideal voltmeter will simply sense the voltage, and diverting no current means resistance is infinite. In real life, this resistance is in the mega ohms range, at least 10 mega ohms, if not more. Typically, like benchtop meters like these will be more than 100 mega ohms. So for all practical purposes, zero currents is flowing through that meter. So it's not taking any energy or power away from the circuit. Make sense? Same thing for an ammeter. Now you have performed current measurements, right? You have to break the circuit and insert the meter in the middle. And so if you wish to connect, this is connecting a voltmeter. This would be connecting a ammeter. So what you would want is to break the circuit, insert the meter in the middle such that the current passes through the meter itself. Right? In order for it to measure, current needs to pass through the meter. Once it passes through the meter, it takes a measurement. But now what have we done? We have inserted a resistor in series with our resistor, with our load resistor. And so that's not desirable. We don't want it to drop any voltage, right? We want that resistance to be as low as possible. So ideal ammeters, in ideal ammeters, we want that resistance to be 0. In real life, it's like milliohms or less, very, very small. And if it's 0, that means it allows maximum current to flow through, and both ends of the terminal, both terminals of the meter are the exact same potential. That means it is not going to have any voltage across itself. R must be equal to 0 ohms. Resistance of the meter must be equal to 0 volts. Okay. All right. What happens here? I don't know why it keeps doing this. Okay. All right. So this is next few slides are simply some additional points about the topics that we have just discussed. So we saw a simple circuit where we have a voltage source, like a source that supplies energy, and we have a load that consumes energy. The sources could be anything, could be a battery, could be a benchtop power supply, could be a laptop charger, mobile phone charger, could be anything that supplies energy is a source. So it does not necessarily have to be a battery. Anything that consumes energy is a load. Load could be LED, could be a fan, could be a HVAC unit, heating and cooling systems, laptop batteries, mobile phone batteries, heaters, motors, LEDs, could be anything. Okay. Now, when we connect any of these components to a source, we use some cables, some wires. In the previous slides, we did discuss the resistance of these wires, right? When we perform theoretical analysis, everything is ideal, meaning the wires are ideal. They don't have any resistance. R is equal to 0. Doesn't matter if it's a short line or a long line. It's all irrelevant. In real life, all conductors have some resistance. Any kind of cable, like even the USB cable that is here on the desk, that USB cable has some resistance, it has some capacitance, it has some inductance. It is inherent to that cable. That resistance, depending on the material of the conductor and depending on the manufacturing specifications, will be either very low or it could rise to the level of interference. So typically, these resistances and inductances and capacitances of wires do not rise to the level of interference. So as a case in point, we have this is, I don't know, maybe like a 3-foot long USB cable, right? If I was to take this 3-foot long USB cable, it'll have some resistance. 5 volts is the power supply line, and then there's the data line that runs through it, right? So if I increase that, if I take that 3 feet long cable, plug it into the computer, connecting some devices or trying to charge a device, it'll work just fine, no problem. But if I increase the length of this cable to 100 feet, then the resistance or the inductance or the capacitance of this cable could rise to a level of interference. Okay, so if the resistance is high enough, then it will slow down the signal or it will block the signal from being transmitted. So you could see glitches that occur in our system. Okay, so one of the effects of having a low quality cable or very long cable is that it will have some resistance that will rise to the level of interference. If it's a power cable or power extension cable, for instance, take a 100-foot long power extension cable, plug it into the wall outlet, and 100 feet away, you would still be able to charge your phone. Because all we need is something akin to like 100 volts coming into the power charger. Your laptop chargers or your mobile phone chargers, for that reason, have a range. It says we can use it from 100 volts all the way up to 240 volts. Line voltage never stays the same. It fluctuates. So even though we say it's 120 volts, it could fall to 110. It could even fall to 100 volts sometimes, depending on the loads. Okay. So even if the line voltage falls from 120 to 110, even to 105, or even 100 volts, your laptop chargers and your phone chargers will still work. If it falls to 90 volts, now they will not. So every laptop charger will have, or every charger for that matter, will have a specification where it states the input range and then the output specification. Okay. So if you take a 100 foot long power extension cable, it might drop the voltage from 120 to 119, but it's not enough to interfere with its operation. But let's say you take a HDMI cable and you run it over 100 feet. So you take a 100-foot long HDMI cable, what do you think? Is it going to work? Probably not, because there are digital signals. You transmit digital signals that are very small voltage or current over very long distances. The resistance or the inductance or the capacitance of that cable is going to interfere with those very small voltages. So the takeaway here is that if you have a very long wire or cable, it depends on the end application, whether it's going to work or not. So the implications of length of a wire is that it will have some resistance, but whether the resistance interferes with its purpose depends on the end application. Okay, if all we are trying to do is obtain a little bit of current and voltage from the power outlet, it'll probably work just fine. If you're trying to run something like a heater, then it's probably not going to work. Okay. So this table here simply shows you the impact of the resistance of real life wires. This number stands for the gauge of the wire. So we have 24 gauge, 22 gauge, 20 gauge, 18, 16. Gauges are weird in that way. The higher the gauge, the thinner the wire. Okay, and the lower the gauge, the thicker the wire. And so columns 3 and 4 show you the typical resistance of a typical metallic conducting wire. Okay, over 1,000 feet, 1,000 meters, meaning it's 1 kilometer long. 1 kilometer long. Or 2 miles. Sorry, not 2 miles. The opposite. 1.6 miles. So 1.6 kilometers in 1 mile. So this is about 0.6, 0.7 miles. Okay. So 1,000 meters is 1 kilometer. So about 0.7 miles. So it'll have a resistance of 84 ohms. So if you run a power cable, plug into a 120 volt outlet, and you connect a cable that's 1,000 meters long, you have a total resistance of about 170 ohms. So a lot of your energy is dissipated on those wires. Okay. Another practical example, real life example. If you have a small appliance that requires a heater, like a heating coil, let's say a toaster or oven or something like that. Let's use a space heater as an example. So if I bring a space heater in here, typically space heaters or electric heaters have very short cables. The reason for that is because the electric heater is going to pull a lot of energy from your power outlet. A lot of energy means a lot of power. A lot of power means a high amount of current. So when you plug a electric heater into your power outlet, it's going to pull a large amount of energy. That large amount of energy being transferred across the wires is going to result in the wires being heated up. Power loss will occur in wire, irrespective of how good that wire is. So if the wire gets hot, what's going to happen? It's going to melt the insulation if it's not designed to handle it. It melts the insulation, then there's going to be bare conductors touching each other, creating a short circuit, and it's going to blow out your circuit. It may even cause a fire to start. And for that reason, manufacturers will not spend a whole lot of money in making those power hungry cables. They make the cable very short so that the power does not have to transfer over long distances. And without fail, all power heaters will come with a warning. Do not use this with power strips. Do not use this with extension cords. And this is the reason why. So if you use it with a power strip, and you use it with an extension cord, that electric heater is now, let's say I use a 10-foot long extension cord. My electric heater is 10 feet away from the power outlet. Power is transmitting over those long distances. And so power loss is going to occur over that long 10-foot long extension cable or power strip. Gets heated up because, again, a large amount of energy is being transferred. And it's going to cause a short circuit. In worst cases, might cause a fire to start. Okay, that's why it's not safe to use extension cables with power outlet. I mean, with heaters. So those are some of the real life implications. Okay, how do we? This is, of course, something we already did. So it's basically, how can we calculate the power loss in the transmission line? Well, basically, we find the current. And if we have the current, apply I squared times R, and you can calculate the power loss in the wires. Okay. Power loss in the wires. So, and we already talked about and discussed this. Some portion of the total power is definitely wasted in the wires. I spoke about this also. It's 11 volts is measured here and here, plus minus. And this 0.389 is also measured with reference to here. Okay. Okay. There are two ways of connecting circuits. We can connect them in parallel, or we can connect them in series. Okay, this shows parallel connection. Excuse me, sorry. And the next slide, thank you, shows you a series connection. Okay. Let's talk about parallel first. Let's start with the real life example that's in front of us. We all see these power outlets. They're on these vertical stands. In the front row, we have 3 of them. Okay. Each stand has 6 outlets. The 6 times 3 is 18. Okay. So there are 18 power outlets in the first row itself. There's another 18 in the back. And there's 5 power outlets in the last row, which is about 5 times 6, so 30 power outlets. All of these outlets put together, they're all connected in parallel. Okay. If you just look at a power strip, or if you just look at the stand itself has these 6 outlets, they're all connected in parallel. Okay. If they're connected in parallel, see. Okay. So if they're connected in parallel, you have 3 wires, right? In each power outlet. There's the neutral or the ground wire. Sorry, the ground wire or the earth wire. Then there's the hot wire, there's the neutral wire. So let's call it ground, plus, and minus. You have 3 wires in each power outlet. All of these connections are tied separately, but in parallel, meaning the ground of each power outlet is connected together. The plus of each power outlet is also connected together, and the minus of each power outlet is also connected together. That's all it is. All circuits, all power outlets are all connected in parallel. If you look at the floor, you will see that these vertical stands plug into a circular outlet in the floor. And all of those circular outlets are also all connected in parallel. We can't see it right now. I saw it because I was here when they were laying out and refurbishing the room. But there are pipes, there are metallic pipes that are running under the carpet. Okay, similar to the ones that are overhead. And these metallic pipes are running from the wall. So if you look at on your far right on the wall, lower than the height of the benches, you'll see that these metallic pipes, they're all connected in parallel. So pretty much every single power outlet in this room, they're all connected in parallel. Anytime you plug in a device, it's all connected in parallel. If someone makes a error at one of the lab benches, it's gonna turn off the power to every single power outlet in the room. So that's by far the most common way of power distribution. So let's use an illustration. If we have a power distribution box, and let's say this is outside the building. Okay, this power distribution box is outside the building, and then we have these rooms inside the building. This is just a very crude, non-technical illustration. So room 1, room 2, and room 3. Okay, you have this cable coming in. That cable is going to all 3 rooms. They're all connected in parallel. But how do we separate it out? Right? We don't want like one small mistake in one of the lab benches to like shut off power to the entire building. So we say we're going to isolate these circuits, and we isolate them by putting them on circuit breakers. So each one of these, and I don't know exactly how these electrical circuits were laid out here, but I'm just assuming that every room is on its own circuit breaker. Sometimes we have multiple circuit breakers inside one single room. So if you ever come by my office space, or in any of the next time you're in a lab, in the lab room, just check overhead. Each one of those lab benches will be plugged into a power, like a circular power outlet that looks very different from our normal power outlets. Has anyone ever noticed that? If you check overhead in any of the lab rooms, not in this one, but any of the other lab rooms, you'll see the lab benches are plugged. There's a long cable, like a long thick cable, and it's going to be plugged overhead into like a circular power outlet. Each one of those power outlets is on a separate circuit breaker, meaning if one lab bench goes out, it's not going to affect the others. And circuit breakers are like fuses, okay? As the name suggests, it breaks the circuit. So in vehicles, in car vehicles, we have a fuse box. A fuse is nothing but a wire. It's a very thin wire, which has, depending on its spec, which can only carry a certain amount of current. If a fault occurs in the end of the line, and it's trying to pull a large amount of current through the fuse wire, guess what? The wire gets hot. Because it gets hot, it melts. And the wire melts, circuit is broken. And we say the fuse has blown out. So you got to take the fuse out, plug a new one in. And so we have to keep a stock of fuses. Thankfully, that doesn't happen as often as it used to. And in critical applications, we just want to flip a switch. So we have circuit breakers. Circuit breakers have relays inside them. So it's a coil that activates. It's like a switch. So as long as there's no issue, it's not activated and the path is closed. If something goes wrong, the relay gets activated and it trips. When it trips, that means it breaks the switch, or it activates a switch. And when it activates it like this, circuit is broken. Hence, we call that device as a circuit breaker. So if you put each individual room on its own individual circuit breaker, well, if a fault occurs in one of the lab benches, it trips the circuit breaker for this room, disconnects it from the rest of the electric power lines, and thus the other rooms are not affected. Okay. So if we want to isolate every power point, we could have an electric circuit breaker on every single power outlet, which would be cost prohibitive, would be very expensive, would make no sense. Yes. Oh, okay. All right. Yeah. So we put everything on a circuit breaker, it would just be, it depends on the application. Depends on the application. All right. So that's one way of connecting. And then the other way is, of course, series. Series connections are very common in remote controls, in wireless devices. Now the batteries are integrated, but anyone ever have a RC, radio controlled toy car or toy vehicle or any other kind of RC control device? There's a battery pack in there. The battery pack is comprised of multiple cells that are connected in series. If you ever change the batteries on a remote control, remote controls typically have like 2 batteries in series. Has anyone ever noticed that? Or changed batteries on a remote control ever? You put 2 batteries in there, right? You put 2 batteries in there, it's never, well, now they are because it's designed, but if you have done the old school style, positive, negative, positive, negative. And there's a metal plate. There's a metal plate that is inside your device. And then metal plate typically has a stud and a spring. Anyone ever notice that? If you have a remote control lying around, you might want to take a look. The stud is where the positive end of one battery is connected, and the spring is where the negative end. So the metallic strip, what it's doing is it's connecting those 2 batteries in series. Okay, so that's one way of making a connection. So on the flip side, that's acting as a source. The reason we connect it in series is because each battery is 1.5 volts. When we connect those voltages in series, they add up. So you get 3 volts out of those 2 batteries. I have a remote control that is 15 years old. It takes 3 batteries. So 1.5 plus 1.5 plus 1.5, total output voltage of 4.5 volts. Okay. And then came along Apple. Apple had some wireless mice where you could change the batteries, and they charged $100 for it because the batteries would plug in this way. So their internal circuitry, they had a wire that would go and make a connection like this. And then this wire would, of course, go out like this. And so you'd get 3 volts. So a normal wireless mouse would cost about $20. Apple wireless mouse would cost about $100 for the design and engineering. Yes. Sorry, what? It's just aesthetically. So question being asked is why did they design like it's aesthetically appealing, I would say. You're just putting two batteries side by side in parallel. So there's a little bit of symmetry. That's all. Yeah, design is wonderful, but I don't like paying that much for design. It's form over functionality. As long as it's functional, I don't care how it looks inside, right? But I do have one. I have a battery operated in my mouse like that in my office. So I'll bring it. Anyway, the point, these are sources, obviously, but the principle remains the same. Okay. You can connect a source, you can connect a load in series or in parallel. If you connect two batteries in parallel, the voltage will remain the same. But now what you're doing is you're increasing the current that you can supply to your circuit. Okay. So when you connect sources in parallel, you can increase the current that is being supplied to your circuit. When you connect sources in series, you're increasing the voltage that is being supplied to your circuit. So it's the same concept. So if you have a single voltage source and you connect it to two loads, the current remains the same. Current through the entire load system is going to remain the same, but the voltage will get divided. When it's in parallel, like this one, the voltage remains the same, but the current is divided. Okay. So review each of these questions and answers. They're already provided there for you. So you should be able to do, from the questions and answers, you should be able to do a bit of self-work. Okay. So we'll end class here today and pick up here again on Monday. Monday's quiz will be based on the material that you have covered in these three Monday, Wednesday, Friday lectures, as well as a little bit on the homework one. Okay. Homework one, again, as a reminder, is due Sunday night, but no penalty until Wednesday. So effectively due Wednesday.